Bodineau, Laure Saint-Raymond, and Sergio Simonella. And so the general question is trying to derive fluid mechanics equations from particle systems. That's a very broad question we'd like to address. But today, except for the introduction, I'd like more to focus on deriving the Boltzmann equation from particle systems. And then it's well known in some sense that you can go from Boltzmann equation to fluid mechanics equations. But okay, so let me just explain a little bit the plan of this talk. So first of all, of course, I'll try to explain what the particle system looks like. We'll look at the simplest possible equations, which are those satisfied by hard spheres, and they're totally deterministic. So I'll just be writing Newton's laws, actually, for those hard spheres. And then we'll see that the Boltzmann equation can be derived from that hard spheres model and can be understood as a law of large numbers in some sense. So I'll try to explain that. And essentially what the Boltzmann equation is telling you is that when the number of particles is going to infinity, then they all in some sense become as if they were IID particles, right? So they are correlated by collisions, right? Those hard spheres are going to collide very often, but in the limit of a large number of particles, in the end, they all behave in the same way and their density satisfies the Boltzmann equation. So that's well known. And what I'd like to explain in this talk are two new results obtained with Laure, Thierry, and Sergio. And those results relate first to small fluctuations. And what we'll see is that we can derive some kind of a central limit theorem. So you see the Boltzmann equation as a law of large numbers. And then the question is, what are fluctuations around this limit? And so what we'll see is that there is some kind of a central limit theorem. And although the initial system of particles is totally deterministic, at this level of small fluctuations, you have some noise appearing, which comes from collisions. So that will be the main part of this talk. And at the very end, I'll give you some insight on what can be done about large deviations. So not small fluctuations, but in some sense, large fluctuations. Okay, so let's start with the model. So what I'm looking here at is a large number of particles, which are all identical. So they'll be hard spheres. I'll call xi the position of those particles, so it's the center of the spheres. Xi is in the d-dimensional torus. Okay, so we'll be in a periodic box, and I is the number, the label of my particle. They're all identical, so actually the label doesn't make too much sense. You just decide how to number them, but everything will have to be independent of that labeling, right? So everything should be symmetric with respect to reordering the particles. So the time derivative of the position, of course, is the velocity. And I'm going to assume here that the velocity, the time derivative of the velocity is 0, meaning there are no exterior forces on my model. So it's really the simplest possible model you could think of. There's no acceleration, okay? Now, of course, this holds as long as my particles don't touch themselves. And epsilon here is going to be the diameter of my particles. Okay, so if my particle number I here has to be at the distance epsilon from particle number j, and this is for all I different from j. And so what can happen, of course, is that this does not happen, meaning that two particles could very well collide. And if that happens, then their velocities jump by the usual reflection laws, elastic reflection laws. Okay, so let me give you the formulas for those laws. You don't have to remember or even to read really these formulas. They're just the normal Huygens or Descartes laws for billiard balls, elastic collisions. Okay, elastic means that the momentum is conserved. Right? The mass of each of my particles is 1, I forgot to say, just to make things simple. So momentum here is conserved and the energy is also conserved. So the collisions are elastic and you can compute the incoming velocities knowing the outgoing velocities or the other way around. By this scalar product, you have the relative distance of my particles, xi minus xj, and the epsilon squared here is just because the size of xi minus xj is epsilon. Okay, and I have 2 of them. Okay. So it's just, this is the easiest model probably you can think of to describe the movement of particles either in the whole space or in the periodic box. And again, here, for reasons maybe I'll be able to explain later on, I'll be assuming my model is set in a periodic box. Okay. Now, as I said, I'm interested in deriving fluid mechanics equations from this particle system. So going from microscopic scales, which are the atoms, to macroscopic scales, which are the average velocity, the average temperature, the average density of my system. Okay, and the idea would be that at the macroscopic level, you should find, in some sense, after some kind of averaging, you should find the Euler equations or Navier-Stokes equations or whatever fluid mechanics equations you'd like, hopefully. And so, as Hilbert actually mentioned in his sixth problem, to go from microscopic to macroscopic scales, one good idea would be to stop at some mesoscopic scale and to use the Boltzmann equation. Okay, so the Boltzmann equation is telling you essentially how many particles at some given time t are at position x plus some small fluctuation dx and velocity v plus some small fluctuation dv. Okay, so I'll call f this proportion of particles. It's a probability distribution, so it's a non-negative function and it's of integral 1. And again, it's telling you the proportion of particles with position x, velocity v at time t. Now, I won't explain or prove in any way why this function should satisfy the Boltzmann equation. Okay, I just don't have the time to do that, but I'll tell you what the theorem can be, what we can prove as a theorem, but I won't prove the theorem at all. So, but it can be proved in some way I'll make precise later, that this function f satisfies the Boltzmann equation. So the Boltzmann equation is written as follows. So I'll just try to go slowly through each term of the equation. So on the left-hand side, what you see here is just a transport equation, okay, which is saying that f, again, depends on t, x, and v, is transported by free flow, okay, velocity v, and that's the gradients in x. So if particles did not meet each other, then you just have this equation equal to 0. Okay, everything's going in a straight line. Of course, that's not true. Particles collide, and I'm only interested here in this talk in binary collisions. I didn't tell you what happens if 3 particles meet, for instance, at some given time, but you can prove that's essentially of measure 0, so that does not happen. The space of initial configurations, which would lead to a three-point collision or more, is of measure 0 in the phase space. So I'll just forget about that. I only look at binary collisions. And the nonlinear term you see here is taking into account the fact that at the microscopic level, particles collide as binary collisions. And here is this term. So it's nonlinear. You have FF here and FF. F prime here does not mean the derivative of F. It means I'm computing F at position at position X, time T, and velocity V prime, where V prime is an incoming velocity. Okay, so what I'm doing here is the following. The right-hand side is telling you if you can create a particle of velocity v, okay, if you have a plus sign, or if you can lose a particle of velocity v, that's if you have a minus sign, okay? So how can you lose a particle of velocity v? Well, what can happen is that a particle of velocity v hits a particle of velocity v1, and you're integrating here over all possible velocities v1. If that happens, then you lose this particle of velocity v, since at collision, the velocity is changed. On the other hand, what can happen is that a particle of velocity v prime is going to hit a particle of velocity v prime 1, okay, and you're averaging against every velocity v1, and that will create a particle of velocity v by those formulas here. Okay, and omega here is any vector on the sphere, telling you essentially what will be the direction, the outgoing direction of your particle after collision. Okay, so this number here I haven't mentioned yet is telling you how strong in some sense the collision is. You see this could be 0. If that's 0, that means my particles have a relative velocity which is parallel to their relative positions, so actually they're not colliding. Okay, so you get 0. On the opposite, this is maximum if v minus v1 the first thing was orthogonal, v minus v1 orthogonal to x minus x1. And it's maximum if it's parallel, v minus v1 is parallel to x minus x1. In that case, you have the maximum number here. Okay, so this is what's called the cross section, is telling you how strong your collision is going to be. And at the end, the other term I haven't explained here is this alpha here. Alpha is a number which you can let go to infinity if you want to find fluid mechanics equations. And this alpha is the collision rate. If alpha is 0, there are no collisions. And the more alpha is large, then the more collisions there are. Okay, so this is the Boltzmann equation, and we're going to see, in some sense, it is a law of large numbers associated with my particle system. So just before we move to that, let's describe a tiny bit more about this Boltzmann equation. And the first thing you can wonder if you see an equation like this is, are there any conserved quantities? So to find a conserved quantity, what you should do is multiply your equation by some test function, let's call it phi, and then you integrate over time, over v, for instance, or v and x, and you see what happens. Okay, and if the right-hand side is 0, meaning if you integrate q of ff phi dv, and if you find 0 for any phi, that tells you that the function f phi, which is still a function of t and x, the integral of f phi, is transported. Okay, and particularly is going to be conserved. Okay, it's just transported by free transport. So in what cases do you get that q of ff times phi is 0? Well, if you use the symmetries of your collision cross-section here, meaning you can exchange v and v1 up to changing omega into minus omega, that will say that you can replace phi by half of phi of v plus phi of v1. You can also exchange v1 into v prime v'1. Okay, and that changes the plus sign into a minus sign. So that explains the minus sign here. Okay, and so if you do this, you have 1/4, which doesn't matter very much. So you see that q of ff times phi is this term here. So if you want q of ff times phi to be 0 for any phi, you need this quantity here to be 0 for any phi. And when is that true? Well, that's true if phi is a constant, okay, because 1 plus 1 minus 1 minus 1 is 0. So any number a would do. It's also true if phi is collinear to v, because v plus v1 is equal to v prime plus v prime 1. And it's also true if phi is parallel to v squared. Okay, why? Because you have conservation of energies. That's also 0. And actually, you can prove that's the only possibility to get 0. So what you see is that this Boltzmann equation inherits the conservation of density, momentum, and energy at the mesoscopic level. So that's one thing we can try to remember maybe. Okay. So what else can you say about this equation? Well, if you do the same computation as I just did, and you replace phi by log of f formally, okay, because you're not sure this is a smooth function at all. If you do this, then using the formula I wrote before, using this formula here, and using the convexity of f log f, what you get is that this quantity here is always non-negative. Okay, minus q of f log of f is always non-negative, meaning that f log f is always smaller at time t than f log f at time 0. This is known as the H theorem by Boltzmann. Of course, you have to justify all those computations, but so Boltzmann had already come up with that theorem, and people were sort of worried about that result because it tells you that the Boltzmann equation is irreversible, right? Because you have this quantity that decays in time. So you can't change the order, the sense of time if the quantity will increase, which is not allowed by the equation. So the Boltzmann equation is irreversible, whereas the particle system is reversible. Obviously, if you change the arrow of time, you just change all velocities into minus the velocity and you get exactly the same system. So you're going from a reversible system of particles to an irreversible equation. So in this limiting system process that will lead to the Boltzmann equation, this has to be taken into account in some sense. You could also wonder, well, what happens when q of f times log f is 0, meaning what happens if you have an equilibrium? Well, if you remember that in that case, your function log f has to be parallel to a constant or v squared, then this is log f. And if you're assuming your f here is a probability distribution, it's an L1, so your c here has to be negative, and what you get is Gaussians, okay, or Maxwellians. So Gaussians are equilibria of your equations. We can try to remember that as well. That's if you're a Gaussian, then you just cancel the nonlinear term, you cancel the grad x term, and you cancel dt. You cancel exactly the equation, actually each term of the equation. Right, so now let's go back to the original problem. My problem is to go from particles to Boltzmann, and especially to Boltzmann, from Boltzmann to fluids, so that in the end I can go from particles to fluids. So as I said before, it is known that you can go from particle systems to the Boltzmann equation. And to do this, you're going to take the number of particles, which I call n here. I'm going to take this number to go to infinity, okay? And at the same time, I should ask for the size of the particles to go to 0, okay? So if you do this with a special scaling, which is written here, then you do converge in some sense. I'll try to make precise afterwards to the Boltzmann equation. So maybe I should say a word about the scaling here. What does that mean? Well, what I'm asking for is roughly to get this Boltzmann equation, what you have to ask for is that each particle, remember, which has a size epsilon, I want it to cross another particle in time 1. Okay, roughly 1 over. So if I do this and I look in time 1, what volume of phase space is going to cover, you see my particle is of size epsilon, and if it doesn't cross anyone else before time 1, then it's just going to follow this cylinder of size roughly 1, if its velocity is roughly 1, okay? So that means that since the diameter of my particle is epsilon, the size of the cylinder is epsilon to the t minus 1, okay? And if I want to be sure if my particle hits another one, The other particles are n minus 1. So I need this to be equal to 1, asymptotically, right? So this is exactly what we call the Boltzmann-Grad scaling here. I need n times epsilon d minus 1 to be 1. Now, the alpha parameter that appeared in the Boltzmann equation is when you assume n epsilon d minus 1 to be alpha. Okay, so if I want alpha collisions in time 1, then this is the scaling I should use. Okay, now to go from Boltzmann to fluids, what you're going to do is let alpha go to infinity, exactly. Okay, what you might do also is even rescale time. So t will become alpha times something. So that means you wait for a very, very long time. And then you do get fluid mechanics equations. At least formally, it's not so hard to see. Theorems are much harder to prove, but there are some results, which I won't describe here, allowing you to go either to the compressible Euler equations. That's if you just fix time, let alpha go to infinity. And then if you let alpha go to infinity, but rescaling time as well, then you're going to recover it in compressible Navier-Stokes equations. Okay, so I won't say more about this because this is not the point of this talk. Maybe the only thing I can say is that what we want to do, right, is to go from particles to fluids. So we need to reconcile both limits, particles to Boltzmann and Boltzmann to fluids. But the thing is, as I wrote here, but I didn't mention yet, Lanford's proof saying that you can go from particle systems to the Boltzmann equation is only known for a very short time. Okay, if my collision rate alpha is roughly 1, then the limit is known for, let's say, 1/2 or 1/4. If the collision rate is alpha, then the limit is known for a time of roughly of size 1/alpha. Okay, but now remember, to go to fluids, I need alpha to go to infinity. So Lanford's proof breaks down because alpha is going to infinity and 1/alpha is going to 0. So actually in this setting, nothing is known, right? In this general setting, we don't know how to go from particles to fluids because we don't know how to go from particles to Boltzmann on a long enough time. So what is known, and this is corresponds to 2 old results by Thierry and Laurent and myself, is in some linear settings, then you can make the whole program work. For instance, on the left-hand side here, you can see that if you take just one special particle, okay, so all my particles are at equilibrium except for one, meaning I just look at a gas at equilibrium and I choose a particle or 2 or 3 or a finite number, and I move it, for instance. Then I let it go. What you can prove is that Lanford's theorem will transform into converging to a linear Boltzmann equation. And then it's not so hard to prove that this linear Boltzmann equation goes to the heat equation. But what's interesting is that the first limit here holds for any time, actually even for times going to infinity. Okay, so that's why you can recover the heat equation to the whole program. The same way, if I take all particles and I assume they're all fluctuations of equilibrium, okay, then you can prove that for as long as you want, as long time as you want, your particle system will converge to the linearized Boltzmann equation, which is known to go to the acoustics and Stokes-Fourier equations at a fluid level, right? So in this situation, you can go from particles to fluids, but it's only linear situations, right? And for a nonlinear situation, no one knows how to make Lanford's theorem better to be able to go from particles to fluids. So since those works, we've been trying to understand more precisely the particle to Boltzmann limit. That was really our goal. And so first trying to understand why the Boltzmann equation is the limit of the particle system as a law of large numbers, a little bit of probability theory. And then we thought maybe understanding better fluctuations around this would make us grasp a little bit more what's missing in the proof to be able to go for a longer time. So that's what I want to do for the rest of this talk. So let's go back to my microscopic model and try to explain a little bit the setting more precisely. So what I'm going to do right now is not fix the number of particles. Remember in the previous slides, we had this capital N, which was the number of particles, which was given. Now, for a mathematical reason, and also maybe for a physical reason, there's no reason to fix N. Mathematically, if you fix N, then you create some correlations essentially in your particles because you're saying their number is fixed, and that creates some correlations between them, and you don't want that. So we're not going to fix N. And from a physical point of view, anyway, you don't know exactly how many particles there are, I guess. So it's reasonable to say that N is not given. It's some parameter which I don't know. So assuming that I have, let's say, if I look at a special type of system where I have N particles, small n, which I don't know, then they all live in this phase space here, which is the particles with coordinates xn. So capital Xn is a collection of all centers of my particles in the n-dimensional torus, dn-dimensional torus. And Vn is a collection of all velocities, okay? And they're in the whole space, Rd times n. And I'll call Zn here the collection of all positions and velocities. And what I have to assume is that the relative distance between my particles is larger than epsilon. So phase space here is a set of all configurations such that if I is different from j, then xi minus xj is larger than epsilon. Okay, so that's my phase space d epsilon n. Right, now what's my initial data? Well, my initial probability density, right? So it's going to tell me essentially how many particles I have and what they look like. What's their density? So if I look at n particles here, then their initial configuration is given by the Poisson law for the number of particles, okay? And I'm going to assume their density distribution is the same for each particle. So their correlation is as small as possible. All I'm asking for is that the number of particles is going to be given by this Poisson distribution, and their position and velocity is given by this function f0, which is again non-negative and a probability distribution. Okay, Z epsilon here is a normalization factor. So if I didn't have the fact that my phase space has holes here, and since f0 is of integral 1, Z epsilon would just be exponential of mu epsilon, right? Now this is not true because I have to, when I integrate this thing here, I have to remember I'm integrating in this domain which is full of holes. Okay, so Z epsilon is much more complicated, but it's still in general a very big number. So why is it big? Because I can compute mu epsilon. If I want to remember I have this Boltzmann-Grad scaling, what I need is that the average number of particles multiplied by epsilon d minus 1 has to be of size 1. Okay, alpha will be equal to 1 here. So the average number of particles, n, calgraphic n here is the number of particles of my model. If I take its average times epsilon d minus 1, this has to be equal to 1. That means that mu epsilon, which is the average number of particles, is equal to this number here. Okay. Now, how do I compute this average? I need to give the definition here because I'll be using this all the time. So the average E epsilon is exactly taking the sum over n. So n going from 0 to infinity of 1 over z epsilon, mu epsilon n over n, the integral of the product of f0 dzn. So the average of anything, let's say any a here, will be integrating this function a. Okay, so maybe we should remember this. Taking the average means taking the average with respect to this initial probability density. Okay, so my number of particles is not known. It's a probability distribution, and the density of my particles is also a probability distribution. Is that okay? Let's try to remember this. I'll go back to that if we need it. So taking the expectation here means exactly E epsilon, averaging against this probability density, right? Okay, so now how do I describe my model at time t? Well, I start with this initial probability distribution and I just push it forward by the flow. And the flow is just this thing here, right? Because the Hamiltonian system behind it is just the time derivative of x is v and the time derivative of v is 0. So this initial probability density satisfies this transport equation, which is very easy. The only difficulty here is that the transport equation is written in this domain, xi minus xj larger than epsilon. So I have to put boundary conditions. So I won't write them here, but the boundary conditions are just saying that if my particles are in a configuration where their velocities are outgoing, then I should replace those outgoing velocities by the incoming velocities. Okay, if my particles, of course, are touching each other. So if xi minus xj is equal to epsilon, with incoming velocities, so outgoing, velocities, xi minus xj dot vi minus vj is positive. That means that the distance is growing, so they're really outgoing. Then I should replace vi minus vj at this configuration by the v prime I minus v prime j. That's the boundary condition for my equation. Right, so what I'm going to be interested in, now we're almost arriving to the Boltzmann equation, is correlation functions. Okay, what Boltzmann is interested in is what's the density, probability density of one typical particle. So to define this, what I should do is take all possible particles. So I'm summing here over p going to 0, from 0 to infinity, and I'm going to integrate over all particles from particle 2 to p plus 1. If p is 0, then you just don't do anything. Okay, and you do that for every collection of particles. That's why you divide by 1 over factorial p here. And this is, by definition, the one particle correlation function. Okay, so you take 1 over mu. Mu, remember, is epsilon to the d minus 1, minus d minus 1. Okay, and you define, this is just a definition, the one particle correlation function by I integrate all bunches of particles, 2, 3, 4, up to infinity, exactly like this. I divide by this combinatorial factor, and this is the definition of f epsilon 0, 1 of z1. Z1 here is in the torus times RT. Right? And now what you can check, I won't do it right now, but it's an easy exercise. That if you take this expected value, which I defined before, the averaging against the initial probability distribution, which was here, right? We're averaged out against this, meaning you sum over n and you integrate against this guy. And what happens is that you can compute the expected value of 1 over mu, the average number of particles, the sum of any function h taken at the initial configuration, sum over from 1 to n, where n is the number of particles. And this is exactly f epsilon 0, 1 times h. In other words, if you look at the empirical distribution, this by definition is pi epsilon of h at time 0. Okay, that's by definition. Then just compute with this definition of the one particle correlation function, you compute this object here. Okay, this is reasonable. This empirical distribution is telling you roughly what the average density of my particles is. And it's translated by this one particle correlation function. And once you've done that, of course, you can also look at 2 particle correlation functions, 3 particle, etc. So you can look more generally at the n particle correlation function. What you do here is you fix n particles, right? And then you want to see how many particles can be associated to those n first, and you integrate against all those possibilities here. And again, you sum from p going from 0 to infinity. And this is a good object in the sense that if you look at a function of n particles, okay, symmetric, you divide by this average here, you take the expected value, you get exactly this n particle correlation function times hn. Okay, so this is really describing clusters in some sense of n particles. Okay, correlations between n particles. Now, where is the Boltzmann equation? Well, here it is. Lanford's theorem, which dates back to 1974, tells you that the one particle correlation function we just defined converges as epsilon goes to 0 or as mu epsilon goes to infinity. It converges to the solution of the Boltzmann equation. That's exactly what you wanted. And that's true uniformly in time, but only on a small time interval. Remember, that's what we said before. And the assumptions on the initial f0 are actually very weak. All you have to know is that it's continuous. And maybe in velocities, you should ask for a bound by a Gaussian. Okay. So this is Lanford's theorem. Lanford tells you a bit more. It also tells you that if you look at the n particle correlation function, which we defined just before, so just look at a set of n particles, this will converge as mu epsilon goes to infinity to n copies of the Boltzmann equation. This is exactly telling you some kind of propagation of chaos, which I was mentioning in the very beginning, because you're saying at time t, when epsilon goes to 0, where the number of particles goes to infinity, at time t, all particles are again identically distributed by this function, which is n copies of the Boltzmann equation. Okay, so that's Lanford's theorem. So where you see irreversibility in this theorem, I told you the Boltzmann equation is irreversible, the original system is not. Well, the thing is, if you want to prove this theorem, what should you do? I'm not going to prove it at all, but let's see. If I take one particle at time t, okay, so this is the arrow of time, I take one particle, and I want to see what happened to it in the past to arrive to the initial data, which was at 0 copied n times, roughly. Okay, if you forget about the exclusion, what produced this particle at time t, z1? Okay, what created this particle z1 at time t at this position and velocity? Well, let's see, if I move back in time, what can happen is that this particle is going to cross another one at some time, particle 2, so it's going to bounce. And then it's going to cross maybe in particle number 3 at a later time, or sorry, backwards before, particle 2, particle 3, and then later, well, before and backwards dynamics is going to cross another particle, number 4, blah, blah, blah. And then at time 0, you have this bunch of, you have this tree in some sense, which is telling you exactly what particles were correlated to particle 1 from 0 to t through collisions. So that's great, but what could also happen is that particle 2 could also cross another particle, let's say particle 5 here, okay, at some time. And what could happen is that particle 5, because it's touched particle 2, it bounces back, and then at some time it could come and cross particle 1 again. That could happen. But that's totally not allowed, because if that happens, that means that particle 5 is going to be correlated to particle 1 at this time here, but actually it already was correlated to particle 1 because of particle 2. So these particles 5 and 2 cannot be independent. Okay, 2 is independent of 1. Okay, it hit 1 and then never saw it again, so that's fine, it's independent. 5 is not independent to 1 because it hit 2, which hit 1. So at this time here, something very bad is happening. And what's very bad here, we call it a recollision. Okay, a recollision is when a particle hits another one, whereas backwards, it had already hit it, or a friend of it, right? So 5 hit 2, which hit 1. So that is totally not allowed. And so Lanford's theorem is actually proving that those events are very little probable. Okay, the probability of such an event is going to 0 as epsilon goes to 0, or mu epsilon goes to infinity, and so you're done and you can prove Lanford's theorem and the Boltzmann equation. But what you can notice here is that a recollision is telling you in what sense time is going, right? Because two particles that recollide backwards are actually colliding for the first time forward, right? Here, particle 5 and 1, if you look at the other way in time, it's the first time they meet. There's no problem. If you look backwards, you're not happy. So the proof of Lanford's theorem is, in some sense, irreversible. So you can make this very precise. I won't go back into this right now, but we wrote a paper with Thierry, Laure, and Sergio, just exactly trying to see and proving exactly where in Lanford's proof and where in the statement of Lanford, you can see that things are totally irreversible. Okay, so let's forget about this right now and try to see why fluctuations can help us. So what happens is that Boltzmann's equation, again, is irreversible because of this entropy decay. This decay of entropy is telling you you're losing information, okay? And so the idea to go beyond Lanford's theorem, to try to do better, is to try to understand where the information is lost. So clearly it's gone into recollisions, because we removed recollisions, we got Boltzmann. So recollisions carry a lot of information. And so what we're going to try to do from now to the end of this talk is try to understand as much as possible where the information is gone and try to lose as little as possible. Okay, so go do better than just Boltzmann. So before doing that, let me just show you why Lanford's theorem is actually a law of large numbers. So remember I had defined this empirical distribution. So at time t, by definition, is just 1 over mu epsilon, the sum from 1 to n, where n is the number of particles, which is random, of a function h, if I compute that at a time h of zi of t, where zi of t is a position of and velocity of my particle I at time t. And this converges to the integral of f, pi epsilon of h converges to the integral of f at time t times h. So that's what Boltzmann tells you. And if I try to rewrite that a little bit differently, I can compute the expected value, as I defined before, of the difference between this empirical distribution computed at h minus f times h, but at a fixed epsilon. Okay, and compute the square, for instance. So what you do here is just expand the square. Okay, so you get my empirical distribution here squared. So either I have I times I, that's h squared, or I is different from j, and I get this term here. Okay, and then if you just compute this and remember that the expected value of this guy is a constant, then you get a minus sign here and this function here. Okay, now if I go on with this computation, what do I see? Well, by definition, this term here is 1 over mu times 1 over mu, the sum of a function of one particle. So it's 1 over mu times the one particle correlation function times h squared. Okay, this term here is 1 over mu squared times the correlation function with 2 points. This by definition is f epsilon 2 times h. And this I don't move, it's just f1 times h squared. Now, if I look at the limit when epsilon goes to 0, what do I get? Well, I know that this guy converges to 0 because this converges to f times h squared, and I have 1 over mu here. This goes away. This here converges to 2 copies of the Boltzmann equation times h, h of z1, h of z2. This is exactly the integral of fh squared. And this converges to the integral of fh squared. So those two things are equal, and then the limit is 0. Okay, so this is a way of seeing Blandford's theorem as a kind of law of large numbers. Okay, so what we're going to do now is try to see fluctuations around that. And remember, how do you get fluctuations? Well, if you believe in the central limit theorem, you should replace the 1 over n, or 1 over mu, sum of h of zi of t, by something slightly larger, by a square root. This should be the good quantity to compute if you want to study some kind of central limit theorem. So that's exactly what I'm going to do here. I multiply everything by square root of mu, and I want to look at the fluctuation field. Okay, so initially the only fluctuations are given by this f0 here. So I want to look at this fluctuation field, and it's not hard. I'm going to show you in the next slide to see that, that this thing converges as epsilon goes to 0 to some functional, and this actually still has some kind of random aspect, since the expectation of this is given by this function here. So actually this fluctuation field initially converges to a Gaussian white noise. Okay, so average is 0, and the covariance is given by this function. Let me show how you get this, because I think the computation is interesting and might explain a little bit what's going on later on. So to understand why this is a Gaussian field, what you can do is compute this characteristic function here and expand this in terms of powers of h. I'd like to get the power 1 of h to be 0. That will tell me that the limit has an average 0. I want the power 2 of h to be the formula I found before, right? And I want all other powers to be 0. If all other powers are 0, that's exactly a Gaussian field. So let's compute this. So I'm going to cheat, of course. So cheating meaning I'm going to assume h is mean free, which is not cheating actually, just to simplify a little bit. That's 0. Especially, and that's really cheating, I'm going to assume there's no exclusion, meaning that my partition functions at epsilon here is just given by the average number of particles, by the Poisson process for the number of particles. Okay, so this is not true, but I'll try to explain why it's not so bad to do that. So let's compute this expected value of the exponential of I, and this guy here is the sum 1 over square root of mu, the sum of h of zi at time 0. Okay, and so we saw it's exactly 1 over z epsilon, the sum over all n's, mu epsilon n to the n, and I integrate my n copies of the initial data, my function, I over square root of mu, the sum of h of zi, and I integrate over zn. And I should integrate in the phase space with holes, but I decide there are no holes to make things simple, so I just have this, which is a mistake, right? But it's much easier. But then this is easy to write because my domain doesn't have any holes. Everything is very easy here because you just have n copies of the same integral. So I have mu n over factorial n, and then I have n copies of f0 of z, exponential I over square root of mu, h of z, dz, n. Okay, so this is actually an exponential, right? So I have the exponential of mu epsilon, the integral of f0 exponential I over square root of mu h, minus 1. Okay, that means I can expand now this exponential here, right? Mu epsilon is going to infinity, 1 over mu epsilon is going to 0. So I just expanded in terms of powers of mu epsilon, and I get lots of terms. The first term doesn't look too good. Why? Because it's f0 I h over square root of mu, which is not nice, but remember h is mean free, so actually this term is 0. Then I have minus h squared over mu, and then I have lots of terms I don't want to compute, which are roughly of size mu 3 halves. Okay, so now what happens? This term goes to 0 because h was mean free. If it wasn't mean free, I should have removed the mean in the definition of the fluctuation field. So there's no, I'm not cheating here. And so you're just left with this term, which is exactly what I wanted, since I get exactly the exponential of minus the integral of f0 h squared of z dz. Okay, so all other terms go to 0. I do have a Gaussian field, and the variance is given by this formula here, which is exactly what I was saying, giving here for the covariance. Okay. Right, so one mistake I did make was assume there is no exclusion. But what's exclusion? Exclusion means that xi minus xj should be larger than epsilon. So the mistake I made was I forgot the terms such that xi minus xj is smaller than epsilon. But the size of such terms is epsilon to the d, right? It's just a volume of xj close to xi. And you see epsilon to the d is much smaller than 1 over mu. 1 over mu is epsilon to the d minus 1. So actually, this error would just go in this term here. So it's not really a mistake. Right, so this is the fluctuation field at time 0. What happens at time t? So I want to look at what happens at time t. So I define this function here, exactly like before. And I remove the average, which is not 0. And I can try to compute exactly the same thing. But what's going to happen here is that the exclusion at time 0, I said, was of size epsilon d, right? What is exclusion at time t? Well, exclusion at time t means my particles mustn't be correlated at time t. What's the probability to be correlated? Well, the probability of being correlated is what we said before, is epsilon d minus 1, because it's the size of a tube in time t. Okay, so it's a particle of size epsilon, which you follow in a tube. And so what you get is epsilon d minus 1. And epsilon d minus 1 was exactly what appeared in this computation here. It was this term here. So at time t, I can't neglect this exclusion. Exclusion at time t means actually recollisions, and I can't exclude recollisions. So what's going to happen, and that's the theorem we're going to prove, is that the fluctuation field satisfies an equation with the initial data I gave you, but in which recollisions appear at order 1. Okay, so here's the theorem. If you look at the fluctuation field at time t, you let epsilon go to 0, then it satisfies this fluctuating Boltzmann equation, which is given by the following. So here, this term here is a linearized Boltzmann operator, which is given here. So it's just transport plus linearizing the Boltzmann equation around the solution to the Boltzmann equation. Okay, so you apply that to function h, you get this thing here. So the fluctuation field is pushed by flow, the flow of course, but also by the linearized Boltzmann equation. So that's one thing. But what happens is that you have a noise, an extra noise here, which appears in the problem. Not just the initial data noise, but a new noise, which is going to come from recollisions. And here's the formula for the noise. So it's Gaussian, the average 0, and the covariance you're going to compute by integrating in time, space, and velocities, 2 different functions, h1 and h2, okay, and your noise at 2 different times, right? And what you get is that it's not correlated in time, you get just 1 time here. It's not correlated in positions, but there is a big correlation in velocities, which is exactly due to recollisions. Okay, I can't really tell you much more, but you see you're really looking at 2 particles hitting each other, because x1 minus x2 is 0, epsilon has gone to 0 here, and this term really is due to recollisions. And actually, so this result was conjectured by Herbert Spohn in the 80s. A lot of people were working on that question, I guess, in the 80s, and people sort of stopped. And so this is a theorem now. You can actually prove that the fluctuation field does converge to this stochastic equation. So let me just give you a small idea about the proof, just the method and the important objects. Okay, I won't give you computations of the proof, but just some important objects. And the most important object in this business is cumulants. Let me try to explain what a cumulant is. So remember we did this computation on the Boltzmann equation, seeing the law of large numbers, by computing the difference between the empirical distribution and the average of f times h. Okay, now let's do the same thing, but with the fluctuation field, meaning it's exactly the same computation, except the fluctuation field is square root of mu times larger than the computation we did for the law of large numbers. Since I do that squared, I'm going to take exactly the computation we did before for the Boltzmann equation and multiply everything by mu. So remember, we had a 1 over mu here, now it's a term of order 1, and we had a term of order 1 before, which is now a term of order mu. Okay. Now by definition, this is going to be a definition, the first cumulant is exactly the first 1 particle correlation function. I call it small f, but it's exactly the same as capital F. It's cumulant of order 1. The cumulant of order 2 by definition is this thing here. What it's describing, what it's grasping is how far from chaos my two-particle correlation function is, right? This is my two-particle correlation function. I remove the chaotic part of f epsilon 2, meaning just a product of f epsilon 1. I rescale by mu, and by definition, this is a two-particle correlation function, right? So if I want to understand at least just the second order here of my expectation, I need to understand the limit of those guys. F epsilon 1, I know its limit, it's Boltzmann. I need to understand the limit of f epsilon 2. And if I want to prove I have a Gaussian field, I need to compute all the powers here. So I need to compute actually all the cumulants. So how do you define the cumulants at order n? So you see at order 2, what I do is I take the two-particle correlation function and I remove the chaotic part f1, f1. If I want f3, what I should do is take capital F3 and remove the f2, f1. When I start playing around with the labels of my particles, I should remove f2 of z1, z2, f1 of z3, and then reorder all the labels, okay? And then add f1, f1, f1. In the end, so this is a formula you don't have to remember at all, but the n particle cumulant is exactly this combinatorics here comes from reordering the number of particles, and then you look at some kind of length of the correlation functions, and you take all products, and that gives you exactly, by definition, a cumulant. Don't remember this formula, but you can maybe remember is that actually you can inverse this formula, and then you can recover the n particle correlation function if you know all cumulants. If you don't like this, you can try doing this at time 0 just by expanding the exclusion condition, right? If I tell you that you want to look at xi minus xj is larger than epsilon for all I and j, let's say from 1 to 3, well, you could say it's 1, nothing happens, minus, well, 2 particles are close, and the other one does what it was, and then I have to reorder which 2 particles are close, plus all 3 particles are close, okay? This will be the 3-particle correlation function, and this will be the 2-particle correlation function, this guy here, okay? The cumulant, sorry, cumulant. So cumulant, if you want to remember something about a cumulant, it's telling you not only that your particles are correlated, but actually they're linked by some kind of chain. Here I have 3 particles which are linked. They're close. All 3 are close. Whereas f epsilon 3, we're not saying they're close. We're just saying they're together. I'm looking at them together. I don't know they're close. F epsilon 3 is telling you they're close. F epsilon 2 is telling you 2 are close. F epsilon n is telling you I have a cluster of n particles which are linked by some kind of chain. Now, how do you construct those guys? So this is just a drawing. I'm not going to prove anything here because it gets very messy. But if you look at n particles, let's say here I have 3, 4, 5, 6 particles, which are the same as here. 1, 2, 3, 4, 5, 6. At time t, I'm going to look at their collision trees, just as we did before with 1 particle. Now I look at all of them, their collision trees, and I want to know if those trees are linked. Not just at time 0, but from time t to time 0. So I just look at my trees. If they're linked, I put them together. Okay, and that's exactly this thing here. And then I say, okay, this one is not linked to that one. Okay, so this tree here is not linked to that tree. That's a correlation. Saying they're not linked is correlating my trees. So I have to say that this not linkage is 1 minus they are linked. And this is what I'm doing here. Okay, so in the end, you do all that and you start computing things. What you find is that those cumulants are actually bounded, and that's an optimal bound. That was not so easy to find, but they're bounded up to some factorial n. So you can find a limit when epsilon goes to 0. Okay. The other thing you can prove is that if you compute, just like we did before at time 0, this expectation of the characteristic function, then you can expand it. That's exactly the computation we did at time 0. You can do it at time t. And you see that if I get a limit for all those guys, then I get a limit for that guy. Okay. And what you see is that because of the square root of mu, since those guys are uniformly bounded in epsilon, then only the 2 first terms count, and that's why you get a Gaussian field. All the others are small, just like at time 0. And now the limit, I won't prove anything, but the limit of f epsilon 1 is exactly the Boltzmann equation that we saw before. The limit of f epsilon 2 is saying I have 2 particles, and if I look at their backward flow, they have to recollide because their trees are connected. So that's why you get a recollision in the limits, right? I told you there was this kind of recollision operator, which is here again. sorry, which are not here, which I wrote before. And this is because I'm looking at a cumulant of order 2, and that's just how it comes out. Okay, so maybe I just have 2 or 3 minutes, or I don't know how much, to tell.
5 minutes.
5, okay, great, it's even better. Okay, so this is essentially the proof of the fluctuation theorem. Okay, of course, you have to work out, the hardest part of the proof is working out this bound here. Okay, once you have this bound, you have a limit and you're very happy. Well, you have to compute the limit, of course, but I won't go more into that right now. But the other thing we were happy about is this factorial n here. Okay, which is optimal. Let me just finish by this. This factorial n was the key that gave us the large deviations principle. So just in the last 3 or 4 minutes, let me just recall what we mean by large deviations principle. What you want to do is, Blanford tells you that your particles typically will follow the Boltzmann equation. And now large deviations are asking, what's the probability to observe something else? Okay, a totally different function. It's not a fluctuation now, just a function phi, which is not f. What's the probability of that? And so you do have a large deviations principle if you can prove that the probability that your distribution is phi, essentially, and not f, is exponentially small with this factor mu, and a function, or functional, of phi. Okay, and this is a large deviation functional. And so what we prove is that this is true, this can be proved, and this function f satisfies a Hamilton-Jacobi equation. And to prove that, we go through, again, the characteristic function, which we rescale again by a square root of mu. This is a very large factor. You take a log, divide by mu. This is known as the cumulant generating function. And so I'll stop here. Once you work on that hard enough, what you get is that this functional here is given by some kind of minimizing procedure, okay? Because you were able to find the limit of your limiting cumulant generating function. And I'll stop here. What you can prove is that it satisfies this very nice, in some sense, I don't know if it's so nice, Hamilton-Jacobi equation. Okay, so the time derivative of this limiting cumulant functional is the Legendre transform of the large deviation functional, and it satisfies this Hamilton-Jacobi equation in infinite dimensions. Gamma here is a function, okay, everything's a function here. And what was nice here is that this Hamilton-Jacobi equation, or rather the Legendre transform of the solution, is exactly the functional that Rizal had found many years ago for a totally stochastic system, not the hard spheres, stochastic dynamics. And Freddy Boucher very recently conjectured it would be the same for the Boltzmann equation, and that's actually what we proved. So what's interesting is that it's also true actually for the fluctuation theorem. It's true for the large deviations. You don't see the difference at the limits between hard spheres and any kind of stochastic approximation, actually. You get the same large deviations, you get the same fluctuations. And so what we hope is that since now we get this full picture with the Hamilton-Jacobi equations and with the large deviations, we hope that we haven't lost any or hardly any information, because the cumulants are really telling you exactly where, or we hope they're telling you exactly where the entropy has gone, because they're really telling you how all particles are linked by chains. And hopefully, if we understand that precisely enough, we'll be able to understand a little bit more large time dynamics maybe, and even maybe where the entropy is going and that kind of thing. Okay, so sorry, maybe I was a tiny bit over time. So thank you very much for your attention.